In many real-world data science projects, one would have to deal with incomplete data. Some statistical or machine learning algorithms either work on complete data or throw error when they encounter missing data. Besides, missing data can influence conclusions drawn from data. This means you, the analyst, would have to pre-process the data, deciding on what to do when some values in your data are not available. This tutorial is a series on handling missing data using the R programming language, and so subscribe and check the next videos. I will not just show you functions but demonstrate how and when to use them and explain why they are being used. I hope to improve your knowledge in R as a programming language and not just as a data analysis software. My aim is to make you see R from both a developer and a data scientist perspective. I am using RStudio IDE for convenience, but you do not need it to follow this tutorial. We will be using the Boston housing data found on Kaggle, and you may download it if you want to use the same data to follow along. Otherwise, use any data of your choice. Let us read our data into R using the read.csv function and assign the result to a variable df. And of course, if you are a fan of the tidyverse package, you can use the read_csv function or the fread function if your preference is data.table package. Run that line of code. I will be clearing the console from time to time using the keyboard shortcut Ctrl+L. When we look at the first few records using the head function and try scanning through the data, we see the presence of missing value. Incomplete data in R are referred to as missing values, and they are represented by NA for not available. Some datasets may use a different symbol or value to indicate data not available. In those cases, first convert those values to NA. Note that the approaches we will be discussing are not limited to a data frame. You may substitute data frame for a list or a vector and you should be fine. We may be dealing with a dataset where the NAs are not easily seen and we do not want to be scrolling or scanning through the data trying to find NAs. In R, there is a way to tell the presence or absence of NAs in our data. We ask if some values in our data frame are NAs using the is.na function. It basically turns our data frame into a logical array or matrix where the entries that are NAs are indicated as true and those not NAs are indicated as false. One setback to using this output to tell the presence of NA is that it is not definitive enough and requires that we scan through to find the true values. It would be nice to have a definite approach or a way to reduce our analysis to just a single value that tells us the presence or absence of NA. One way to achieve this is to sum the values in the logical array. This is possible because R internally coerces true to 1 and false to 0. So basically, we will be summing zeros and ones. If the sum results in 0, then all the values in our logical array are false, and thus there is no NA or missing value present in our data. However, if the sum is greater than 0, then there is at least one value in the array which is true, and hence NA is present in our data. Let us implement this. Sum the output of is.na, run it, and we get 120. This result gives us two important information. First, it tells us there is a presence of NA since the sum is greater than 0. And second, we precisely know the number of entries or values in our data that are NA, 120. Note that this is not the same as the number of rows that have NAs. It just says we can find 120 NAs in our data, regardless of where in our data they occur. Let us run the previous code to get our logical array again. What do you think would have happened if we had summarized our logical array by finding the mean of the values? The mean function also does type coercion where possible, and just like the sum function, it coerces true to 1 and false to 0. So we are essentially finding the mean of zeros and ones. This time, we get a proportion of our data values that are NA, which is approximately 2% of all the entries. Like the sum approach, a mean of 0 would have implied no NA. Let me comment on the speed of the approaches we have considered so far. Realize that the is.na function on our data frame can be expensive, since all the entries of the data frame would have to be investigated and tested for NA. A data frame with a lot of entries will imply a lot of NA checks. Also, using the sum function requires that all the entries of the logical array be added. We just need a sum greater than 0 to conclude that NA is present. So, at the first instance of true, which means sum equals 1, should have been enough for us to make that determination. But that is not the case. Can you imagine the memory load if there are a lot of values to sum? In addition, finding the arithmetic mean of values can be worse for speed purposes. We first need to sum all the values and then divide by the total number of entries. If we just want to know whether our data has NA, then I will not recommend using either the sum or the mean approach. Let us consider another approach. We can use the any function to test if at least one of the values in our logical array is true. This expression returns true if NA is present in our data and false otherwise. In our example, there is NA in our data and hence we get true. This way of deciding on the presence or absence of NA can be useful if you want a true or false output to use in a code. For instance, if you have a model that only consumes complete data, that is, data with no NA present, you can decide to continue using the model if any is.na returns false, or otherwise stop or use a different model. Another reason to consider this approach is that the any function immediately returns true when the first instance of true is found in our logical array, and hence, unlike the sum or the mean function, it does not necessarily consider the entire logical array, and this can be faster. The R statistical language has possibly faster way of implementing any is.na approach. The function is called anyNA. We can implement it as anyNA and pass the data frame as an argument. When we run it, we get true, indicating the presence of NA, which is the same result as before. The last approach I want us to look at uses the location of the values within the data to tell if NA exists. Basically, if NAs exist, then there is a function that can tell us the indices or location of the NA values in our data. If NAs do not exist, then such indices cannot be found. The which function tells us the indices or location within the logical array of is.na that are true. I set the array.index argument to true because I want both the row and column indices of the true values in the logical array. If you just want the indices in a column major order, then leave the arrow.index argument as false. Let us run it. Scroll up to the top. We get a matrix. If there were no NAs, this matrix would have no entries. However, we read that there is NA at row 54 of column 1. And we can scroll down to see all the indices. This approach gives us all the rows in our data that have NA and also all the columns of our data with NA values. Of all the approaches, my preference is the anyNA function. It is concise and faster. But depending on the analytical question at hand, I use the approach that gets the job done. For instance, if counts of NAs are needed, then summation may be the way to go. If you found this tutorial useful, please consider subscribing. Thanks for watching.